Everyone. Okay, today it's a great pleasure to have Aneeq from University of Illinois Urbana-Champaign, who is working with Tamer Bashar, if I'm correct. And so today you are going to present on reinforcement learning for linear quadratic meaningful games and multiple populations. So thank you very much for accepting the invitation, and the floor is yours.
Okay, thank you. Thank you for joining, guys. Today I'm going to present RL, reinforcement learning for basically mean field games in multiple populations. And this is joint work with Eric Mealing in our group and Professor Bashar. So let me start the presentation. So just an outline of the presentation. I'll start with some motivation of our work, some background on linear quadratic mean field games. Then I'll move on to multi-population linear quadratic mean field games. Then I'll show some existence and uniqueness results for the non-stationary equilibrium of the mean field game. Then I'll move on to the epsilon Nash guarantees for the mean field equilibrium, basically how they apply to finite population games. After having done that part, then I'll move on to the RL part, which will be zero order stochastic optimization based RL, and also present what's the motivation for using zero order stochastic optimization techniques for RL. Then I'll present some finite sample guarantees and then a short numerical analysis. Okay. So the motivation for this talk is a battlefield setting. So I was involved in a grant which was aimed toward battlefield scenarios, and model battlefield scenarios require heterogeneous agents to learn via interaction with the environment. And our goal is to enable a large number of heterogeneous strategic agents to learn essentially consensus and formation control behaviors in a model-free manner. And the contribution of this work is a development of a learning algorithm for the mean field games using zero-order stochastic optimization techniques. And we demonstrate that the multi-agent RL in large heterogeneous populations can be effectively addressed by the mean field game framework. So, moving on, just a very brief literature review of linear quadratic or mean field games, and then linear quadratic mean field games in particular. The work was started by Huang et al. And Lasry concurrently in 2006-2007. And then linear quadratic mean field games is an important benchmark in this mean field game literature. It was the earliest works were in continuous time setting, and then the interest in discrete time setting became more interesting due to applications for RL and other settings. So the first works which had finite sample analysis for RL for linear quadratic mean field games was in stationary equilibria by Fu and his group, and then we extended that to non-stationary equilibria. So the difference between stationary and non-stationary equilibria, I think the way I think about is that the stationary equilibria is when infinitely many agents have achieved equilibrium, and then one agent or single agent is joining this game where there are infinitely many agents which have achieved equilibrium or a steady state in some sense, whereas a non-stationary equilibrium is something like if there are infinitely many agents, but they're just starting the game, so there will be transients in the equilibrium. So that's I think one way of looking at stationary versus non-stationary equilibrium. Then I move on to the mean field games over networks, and there are two kind of works or research areas which people have worked on. So the first one I call mean field games on networks, and that is basically when the agents, decision-making agents, they are traveling over a network. So there are a couple of works by Camilli and Marchi and Aktu, and you can think of it as as a flow of infinitely many agents or a distribution of agents over a network like a road network or a network of that sort. And then the agents, the dynamics and the cost functions of the agents are dependent on the nodes that they are on. The second work is I call it networked mean field games, and basically the agents in this game are coupled via network. So the network enters in through a coupling, and I think the earlier works were the Erdős-Renyi graphs. People used mean field games over Erdős-Renyi graphs by Delahou, and of course works on graphon mean field games by Peter Keynes and Huang, and there are a lot of work since then on graphon mean field games. And we had a recent work on mean field games on multigraphs, which is a slightly different take on this setting. So I think working on or doing RL for network mean field games is hard because you need some sort of symmetric condition on the interaction model. So basically, if you take graphon mean field games, each agent will have a different interaction with the other agents. So generalizing that is a bit hard. I think in the multi-population setting that I will present today, that it's a way to do things which is easier for RL to work on. Okay, so that was the literature review, and the contributions in our work is we'll start by formulating the multi-population linear quadratic mean field game, where the agents are partitioned in heterogeneous populations. Then we present existence and uniqueness of the mean field equilibria and a certain structural property. So the existence and uniqueness is established under standard conditions like controllability, observability. And then we also prove that there is an affine structure in the mean field equilibria, meaning that the controller and the mean field trajectory are affine. And I will kind of explain what that means in the presentation. The epsilon Nash, then we present the epsilon Nash guarantee for the mean field equilibria, which means that the mean field equilibria will be epsilon Nash in the finite population setting. Then we'll present a provably convergent RL algorithm using zero-order stochastic optimization techniques. And so these techniques give us a truly model-free method. And what I mean by truly model-free is that given the information in this RL algorithm, the information available to the agent cannot construct its own model. So basically, we only assume access to the cost that the agent gets. So under this setting, the agent cannot construct its own model. So that's why we call it truly model-free. And we also assume access to a centralized, although a noisy simulator that simulates the aggregate behavior of the populations. So next slide. So starting with just a quick background on linear quadratic mean field games, we assume that the agent has linear dynamics and it has an independent zero mean Gaussian noise. And the agent has local information, so that makes it a bit hard for the agent to compute the Nash equilibrium. And the agents have coupled cost functions. So the dynamics has no coupling, but the cost function has a coupling. And the reason we chose this model is that we were assuming a formation control application. So in that application, we have typically cost functions which are coupled, but the dynamics are generally not coupled. So the cost function, the first couple of terms are regulation terms, which are like standard LQR terms. And the second term is a consensus-based term where each agent aims to get close to the average state of the other agents. So this can also be thought of as a consensus where the agent is trying to form consensus with the rest of the agents. In this game, we assume that AB is controllable and A square root of Q is observable. The matrices Q and CZ are semi-positive definite, and CU is positive definite. And now we can present the epsilon Nash equilibrium definition, which just basically means that if there is an epsilon Nash equilibrium, then each agent individually only gains at most epsilon by deviating from that equilibrium. That's like a very standard epsilon Nash definition. So moving to the infinite game, the mean field game, now we only consider a generic agent, and we don't consider a particular agent. This is a generic agent in the infinitely many, in the population of infinitely many agents, and it has an independent Gaussian noise, zero mean Gaussian noise. The agent still has local information, and now the aggregate behavior of the infinitely many agents is represented by a mean field denoted by z bar, and the agent's cost function is coupled with the mean field. And again, there are the regulation terms and the consensus term where the agent aims to get close to the mean field, which is the aggregate behavior of the other agents. So now we can define the mean field equilibrium in the mean field game. Mean field equilibrium is always a tuple, a pair of a controller and a trajectory. Before defining mean field equilibrium, we can define two operators, which is pretty standard in mean field literature. The first operator is lambda, which is also called the consistency operator, and it basically produces a mean field consistent with the controller phi. So basically, it means that it's if we are given a controller, then infinitely many agents. If these infinitely many agents follow this controller phi, then the mean field or the aggregate behavior that will be generated will be z bar. So that's the consistency operator. And for optimality, this is a different operator phi or psi. And what it means is, given a mean field, what's the controller which is optimal for this mean field. And then the definition of mean field equilibrium is finally just the composition of these two operators. So the equilibrium controller phi star is optimal for the equilibrium mean field trajectory z bar star, and then the z bar star is consistent with operator with a controller phi star. Sorry, was there a question?
I have a quick question, maybe if you don't mind. Sorry.
Sorry.
In the consistency condition, the function phi t is a function of the mean field only, so it's not a control for an individual agent, or is it? Like the state of the agent does not enter in phi. So what is the interpretation of phi here? The function.
Phi is a controller. So phi. Okay. So this. So the reason we can write it like in a linear form is basically due to the linear structure of the dynamics. So phi is a controller which can be distributed, but it can depend on the state of the agent and also the mean field. But if you have such a structure and then you compute the aggregate behavior under this controller, you can get this like a linear structure. In essence, yeah. So it depends on the state of the agent and also on the mean field. So to answer the question, yeah.
I see. And so phi t of the z bar t is like the average control or something like that, and that's how you determine the average behavior. Okay.
Yes.
Thank you.
Yeah, I think so. Yeah. So there's also, I think, a question about whether it depends. So phi can lambda can also depend on z bar. Right, so it can go from controller and a mean field to another mean field. But the way we define it here is just phi to z bar. So in essence, it has to be like a fixed point of the mean field. If you get it right. So
okay, thank you.
Yeah. Thanks. Okay. So in literature, there are results on existence and uniqueness of mean field equilibrium under standard assumptions, and then these mean field equilibria are shown to be epsilon Nash. So basically, if you get the mean field equilibrium controller phi star, and then you stack it n times, and then you give it to n agents in an n player game, and that equilibrium will be epsilon Nash. So basically, the best they can do by deviating is order of 1 over square root n, and this epsilon goes to 0 as n goes to infinity. So that's like standard literature results. Moving on to multi-population mean field games. Now the agents are, so this is still, we start with the finite population setting in a multiple population. So there are L populations in this game, and each population has n sub L agents. And then these L populations are connected via a sparse graph. And each agent has linear dynamics, and this is also uncoupled because we are considering like a formation control problem. And the noise is also independent, zero mean Gaussian. Each agent is assumed to have local information. And now the cost is a bit more complicated, but it's very similar in form. The first couple of terms are, again, regulation terms. This third term is called intra-population consensus. So basically, each agent wants to form consensus with other agents in its own population. So this is the aggregate of other agents in its own population. Sorry. And then the last term is called interpopulation consensus, where the agents aim to achieve consensus with the agents of neighboring populations. So these are this L signifies the neighboring populations. And then also we assume that there is some kind of difference of opinion term. So if we call this a consensus, each agent might choose to have difference of opinion with agents in other populations. So this is kind of the multi-population mean field or multi-population finite agent game still. And we can define the epsilon Nash equilibrium in a very similar way, where each agent individually deviating with at most gain epsilon. Now we can go to the mean field limit, where we take n sub L, where the number of agents in each population goes to infinity, but the number of population is still constant, and it's still connected via a graph. So the generic agent in population L has linear uncoupled dynamics, independent zero mean Gaussian noise. Each agent still has local information, and now the coupling comes into the costs to this mean field term, where this is aggregation or concatenation of the mean fields of all the different populations. And then we can write it down as essentially like a track and control problem, where each agent inside the population wants to have consensus, and outside the population with its neighboring population can choose to have this difference of opinion. And of course, these are regulation terms, intra-population and interpopulation consensus. So now we define the mean field, the equilibrium of this mean field game in multiple population. And again, we define two operators. The first one is consistency, and the second one is optimality. The consistency operator is given controller, it outputs a mean field. And this is basically, I'm sorry, it should be, oh, sorry, that's fine. So given a set of controllers now this is a set of controllers phi, so one for each population, and then it outputs the mean field, and the mean field z bar is a concatenation of the mean fields of all the populations. And then the optimality operator is the converse, which is given the set of mean field z bar, it outputs a set of controllers phi. Set of controllers phi, yeah. So which is the best response to that mean field. So these are the consistency and optimality operators, and now we can move on to the definition. The definition of mean field equilibrium is again the tuple phi star and the z bar star, where phi star is optimal with respect to z bar star, and z bar star is consistent with respect to phi star. So this is just the definition of the mean field equilibrium. So now we present our first result of the work. And basically, we can show existence and uniqueness of the mean field equilibrium under fairly general controllability and observability conditions, where we say that if AL, BL are controllable and AL and square root of QL are observable, then we can show existence and uniqueness. And also we show a certain affine structure in the mean field equilibrium. So if you see, so this is the equilibrium controller under in the mean field, and this is the equilibrium mean field trajectory. So the equilibrium controller has these linear terms. In the controller, the terms involve terms which are linear in the state of the agent, and then the linear in the mean field. And similarly, in the mean field trajectory, this is the dynamics of the mean field trajectory has affine form, where the first term is linear in the mean field, and then the second terms in this equilibrium are the controller has a control offset term, and the mean field also has this kind of a mean field drift, and these offset terms are due to the difference of opinion. I just want to be clear. So let me go back. So there are these difference of opinion terms in the interpopulation consensus, and these cause the offset terms in the equilibrium, the controller and the mean field trajectory. Okay, so just an outline of proof. First, we prove that the mean field trajectory at equilibrium, there is existence, uniqueness, and affineness in the mean field trajectory. And this is proved using the probabilistic approach, and which leads to a Riccati equation in standard form, and then proving existence and uniqueness of the Riccati equation solution leads to the existence and uniqueness of the mean field. And that Riccati equation can basically we can get the existence and uniqueness of solutions using controllability and observability assumptions that we referred to earlier. And once we have proved the existence, uniqueness, and affineness of the mean field trajectory, we can do the same for the equilibrium controller by formulating the problem as an LQ affine tracking control problem. So that's pretty much the outline of proof. Now, what are the implications of the proposition? The first implication is that at equilibrium, the mean field has deterministic affine dynamics, so it can be computed offline. And secondly, the controller is causal and it's distributed and affine. So the causal controller allows for reinforcement learning in the non-stationary setting. So if the controller was non-causal, the mean field game incorporates a tracking control problem, and for a general tracking control problem, the controller may not be causal. It needs to have access to the tracking signal in the future, right? So, but in our setting, we were able to show that the controller is causal, and this causal controller allows for reinforcement learning in the non-stationary setting of our work. And this is the kind of one of the main contributions of our work. So let's move forward. So let's move forward to the epsilon Nash guarantee, and then after that we can move to the RL algorithm. So the epsilon Nash guarantee is pretty similar to the epsilon Nash guarantee of the single population game, where each agent can at most gain this epsilon if it deviates from the equilibrium. And this epsilon is interesting, and what it depends on is for each agent. Now, this is for the finite population game, right? So the epsilon Nash guarantee is for the finite population game. Each agent n in population L. Basically, the epsilon for this agent will be a minimum over the number of agents in the neighboring populations, and also the neighboring population also includes its own population, the agent's own population. So basically, if the number of agents in the neighboring populations goes to infinity, then the mean field equilibrium will approach the Nash equilibrium. So that's the epsilon Nash guarantee. And just a short proof outline. The proof relies on quantifying the difference between the equilibrium mean field trajectory and the empirical mean field trajectory, where the empirical mean field trajectory is you can think of it as If there are finitely many agents and they apply the mean field controller, then the mean field trajectory that's generated we call it empirical mean field. And we can show that the steady state distribution of the difference depends on NL, and the difference goes to 0 as NL goes to infinity. And the applications are standard that mean field controllers are epsilon Nash in the finite population setting, and the epsilon it depends on the min over the set of neighboring populations. So now we move on to the RL part for the multi-population mean field games, and in this presentation, I'll present RL algorithm, which deal with this in literature, RL algorithms for linear quadratic mean field games typically deal with stationary equilibria, and they mostly work with single population setting, and they're not truly model free, so the model can be reconstructed from the inputs, and under certain conditions in literature, there are results which show that model-based RL is better than model-free RL. It's faster. So if you don't have access to that information, you can have model-free algorithm. So the mean field, the affine structure of the mean field equilibria that we just proved inspires a two-part RL algorithm. The first part, it's pretty intuitive. The first part deals with approximating the linear components, and the second part deals with approximating the offsets. There's a slight intuition in this kind of two-part structure, and I will explain it later. Each agent L there is one agent L for each population, and it's unaware of the dynamics of its dynamics and cost function, and the agent only has access to noisy estimate of the controller cost. Now, zero-order stochastic optimization-based RL is basically a stochastic gradient descent, but the gradient is not. It is basically computed using a smoothing procedure, and we call it a smooth gradient, which is computed using noisy estimates of the cost. So this problem can actually be formulated as a drifted LQR problem. So, and the reason for that is in proposition 1, we prove that the equilibrium mean field is affine dynamics. So we only consider mean fields with affine dynamics. There is a certain noise that creeps in due to imperfect simulation. I'll show why. The simulator that we use is assumed to be imperfect and slightly noisy. So under this affine mean field, we can define an extended state of each agent L, where we just concatenate the state of the agent with the mean field. Under this concatenation, we have extended state, which has linear drifted dynamics. So the dynamics are linear, but there is a drift term and also the noise. And then the cost of each agent L kind of becomes a tracking cost with the constant tracking signal. So this problem becomes an LQR with drift and a constant tracking signal. So that can give you an intuition of how we can solve the problem in RL setting. So for this RL algorithm, we search in the set of affine controllers because the optimal controller for LQR with drift will be affine. And the cost under an affine controller, it can be broken down into two parts, well, three parts essentially, but the third part is constant, so we don't need to care about that. The first two parts are interesting. The first part is actually the LQR cost, or the standard LQR problem. And if we can somehow set the control offset and the dynamics offset to 0, basically setting the offset terms to 0, then we get the LQR cost. And the second interesting part is that for the second part of the cost, if we do argmin over the KL2, which is the offset of the controller, that is independent of the linear part. So basically combining these two pieces of information, what we can do is the linear and offset terms can be learned in a decoupled manner and independently. And then a bit more information about the cost functions. And the cost function satisfies local smoothness. So the first cost function satisfies local smoothness, slipshiftsness, and gradient domination. And the second cost function satisfies local smoothness, slipshiftsness, and strong convexity. So, so now the RL algorithm, we know that we can divide into two parts. The first part estimates the linear terms. The second part estimates the offset terms. And in both parts, each agent uses zero-order stochastic optimization to estimate the controller parameters. So once each agent has updated its controller using ZSO, the centralized simulator computes the mean field under this set of controllers. And in the first part, we only deal with the linear terms, control offset, and the mean field offset. So by setting the control offset for each agent to 0, the mean field offset, we will show that it will for sure be 0 as well. And in the second part, we keep the linear part in the controller constant, and we just change the offset terms in the controller, and then due to that, the mean field offset also changes.
Sorry, can I ask you a quick? Yes, can I ask you a quick question, please?
Yes.
But maybe it is on the next slide. Actually, it was about the simulator and about what is visible from the agent. So what does the agent need to observe in order to do this algorithm? But maybe you're going to answer that.
Yeah, I think so. Yeah, let me go through this slide, and then I think probably will be in better shape. So now just a little bit about the centralized simulator. Centralized simulator simulates the behavior of a single agent in each population, and the behavior of single agent can estimate the mean field. So it's a noisy estimate of the mean field. And so by in essence, we should simulate infinitely many agents, but we assume that we don't have access to this infinite agent simulator. So we have access to the single agent simulator, and using this we can estimate the mean field dynamics. And under a controller phi L, the mean field of population L will have these this dynamics, which is kind of linear in nature. And if the linear controller, if the control offset in phi L is kept 0, the resulting mean field has a linear Gaussian structure. And so this is what we do in the first part. We keep the control offsets to 0, and we get a linear mean field in return. And in the second part of the algorithm, the controller is affine, so we change the control offset, but we actually keep the linear part of the controller constant, and we are changing the offset, and due to that, the mean field will have this affine structure. So did I answer your question, Matthew?
I think almost. Thank you. So my question was, at each iteration of the algorithm, in order to implement the zero-order optimization, what do you need to observe? So the agent observes the reward. So the agent chooses two controls. The K1 and K2, and observes the associated reward, as well as its new state and the new mean field state, or not the mean field state, just its own new state, and then based on that, it tries to learn the gradient.
Yeah, so the agent looks at the cost that it gets for a controller, and also mean field for the mean field trajectory. So basically, we need a long run mean field trajectory over which we can compute the cost. Yeah. I think maybe we can have a discussion after that.
Okay.
So now finally the RL algorithm, which we talked about a lot. So let me just go real fast into it. So this is the first part of the algorithm where we're estimating the linear terms. We initialize the algorithm with K1 L1. So this is the linear part, which is stabilizing. So this is we need a stabilizing linear part, and then the offset part is kept to 0. And we assume that initial mean field trajectory is also 0. Now, in each iteration of the first part, the agent updates its linear controller using this ZSO algorithm. And once it has updated the controller, the simulator updates the linear mean field. Right. So that's the first part. And in the second part, we do the same thing for the offset term. So now after this part, the linear part of the controller is kept constant and only the offset part is changed. So first we initialize the offset part. And then using ZSO, we update the control offset for this given mean field. And then the centralized simulator updates the mean field offset. So that's pretty much the algorithm. So it's just a little bit more details about the ZSO algorithm. ZSO is a stochastic gradient descent algorithm, and in this SGD, we compute the smooth gradient of the function of any function. So this is any function, and we are doing stochastic gradient descent, and this is done using k perturbations, each with norm r. So we generate k perturbations at a given point with norm r, and then the smooth gradient is just the value of this function at these perturbed points, and using this formula. So this is the smooth gradient, and once you have obtained the smooth gradient, we move along the direction of the smooth gradient at a learning rate theta. So the parameters of the ZSO is that the perturbation norm, which is also called the smoothing radius, the number of perturbations that we generate in each iteration, which is the mean batch size, the learning rate denoted by eta, and the number of iterations of the algorithm. So by decreasing the smoothing radius, we can decrease bias, but that actually increases variance of the smooth estimate. To reduce the variance, we can actually increase the mini batch size. And so we can reduce the variance of the smooth gradient using the mini batch size by increasing mini batch size. Learning rate, again, is, as always, is a trade-off between stability and speed. We want to keep it fast, but not so fast that it compromises the stability of the algorithm. And then by a higher number of iterations R, we essentially should get better convergence. Now, actually, this algorithm is a single point, 1 point ZSO algorithm. You can also apply a 2-point algorithm, which has better variance properties. So I was having a discussion with one of my friends, and he pointed it out that you can have a 2-point algorithm which has better variance. Okay. So the first of the lemmas for the proof of convergence of RL algorithm, we prove that the ZSO for the linear controller will converge, given that these the number of iterations, the smoothing radius, the mini batch size, and the learning rate are set in a particular manner, and basically it can be proved using results from literature. And the proof depends on properties of the cost, the first part of the cost. The second part we had to prove ourselves because we couldn't find the proof in literature, and again you have to set the number of iterations, the smoothing radius in mini batch size to be the right quantity, and then you will get basically epsilon convergence to the offset terms in the controller. And just a short outline of proof. The proof was a bit hard to prove because of non-convexity of the set of controllers. And it relies on defining sublevel sets. And by defining these sublevel sets, we can ensure that these local smoothness, slipshiousness, and convexity properties are satisfied, and also the cost doesn't go to infinity. And then we quantify the error between the smooth gradient and the exact gradient, and then we ensure that if the step size is bounded, then basically these quantities are satisfied. These properties of the cost function are satisfied, and then the convergence follows due to strong convexity. Finally, the main result of the paper, the finite sample bounds for our algorithm. So the theorem says that if the number of iterations of the first and the second algorithm, of the first and second parts of the algorithm are kept are a certain number, then and the error accumulated during the zero order stochastic optimization is kept small enough, we can get epsilon convergence for the linear parts. And then if the epsilon convergence of the linear part is small enough, then we can also get epsilon convergence for the offset parts. So these are this is the main result of the paper. And again, this relies on some properties of the, so basically, in essence, it relies on the contraction mapping property of the mean field update. Just a brief outline of the proof. The proof again consists of two parts. First part deals with the linear term, second part deals with the offset term, and relies on the convergence of the first part. There's an estimation error in the zero-order stochastic optimization, which can cause asymmetry in the computed mean fields. But by bounding the error of that is accumulated in the zero-order stochastic optimization, the asymmetric error of the mean field is also bounded. Then we characterize the mean field update for both parts of the algorithm, and then the convergence is proved using the contraction property of the mean field update. Finally, we also come up with a global constant for the cost function. So the cost functions have these properties of flexiousness, smoothness, and gradient domination and convexity, strong convexity. We also proved that the global constant for these properties also appear, and we characterize them. So, okay, so that's the theoretical part of the paper. Then we also had some numerical analysis for our paper, and what we did was we simulated the algorithms for three populations. For one simulation we had a chain network. For the other simulation we had a ring network, and we did a couple of simulations for each of these two networks. And what we saw was that, so the state and action spaces are scalar for this particular simulation. And we saw that the error decreases pretty fast in the first iteration. So if you can see the error for the chain and the ring network both, we saw a fast initial decrease in error. So this is the iteration of the outer loop. And in the inner loop, there will be also multiple iterations going on. So the error decreases very fast in the first iteration, and then from then on, there's a steady decline in the error, and also the standard deviation. So we did this over a couple of different simulations. I think there were 100 simulations that we did for each of these. So basically we saw a good performance for this RL algorithm, and in the ring network, the error was a bit smaller than the chain network, but overall the performance was pretty similar. Yeah. Okay, so just in conclusion, we have addressed the multi-agent RL from a mean field game perspective. The mean field game involves heterogeneous agents in grouped in populations. We have established existence, uniqueness, and affine structure of the mean field equilibrium, also the Epsilon Nash guarantees. The affine structure inspires us with a two-part RL algorithm, and then using zero-order stochastic optimization techniques, we can give like a finite sample convergence guarantees for the algorithm, and then we provided numerical analysis for the three population setting. Yeah. So that's the end of my talk, and yeah, if you guys have any questions, then you can go ahead.
Thank you very much for the nice talk. Let's see, other questions. Yes, Jean-Pierre, I think Jean-Pierre Fouque is pointing out relevant work for MFG with groups and subgroups.
Hello. Yeah. Yeah, I'm pointing out to the work of my student son, who did some work on mean field game. In particular, is looking at the difference between open loop and closed loop. One question in your RL part of the talk, you assume something on the model, right? You know that the model is linear quadratic.
Yes, we are assuming linear quadratic. Yeah.
So it's not model independent. Okay.
Yes.
Right. So maybe what you are pointing out, Jean-Pierre, is just to make sure I understand correctly the question and the answer is that it is not model free in the sense that you make an assumption on the form of the controller.
Yes.
I mean, you kind of know the form of the optimal controller, but you don't know exactly the parameters of the dynamics
Yeah.
of the cost function.
Yes. Yes.
Okay. But you could still use the same algorithm even if the model was not linear quadratic. Maybe it wouldn't converge, but you could still use linear controllers, whatever the model is, right?
So you use an affine controller even if the model is not linear quadratic.
And maybe the proof, maybe there is no proof of convergence, but you can still,
I guess,
you can still
I
use
think
the
you'll have
algorithm.
to, in essence, it's a stochastic gradient descent. So if a gradient descent can converge to a global or even local optima, then I guess you can prove somehow that, I think that'll be an interesting thing. Not sure.
I mean, when you replace the control by a neural network, you don't know that the optimal control is of the form of a neural network, right? You just use this class of controllers and hopefully converge to a good local optimal.
Right. That's true.
But
but using a linear quadratic structure, we have much nicer, I guess, theoretical results.
Yes, of course.
Using so we have a nice structure of the cost and thanks for the question. I'll take a look at the work. Yes.
Okay. More questions or comments?
Hello, thanks for the talk. So
Hi.
I believe you mentioned at the start that you were considering sparse graphs. Right. So have you looked at all at when you have dense graphs that might be larger than just a few nodes, or is that future work?
Let me go back. Let me actually go. Right. So sorry, your question again. So you mentioned that.
I think that you mentioned that the graphs you were considering were sparse graphs. Right. And I'm just wondering if you looked at all into dense graphs.
No. So we consider like a general graph structure. So a general finite graph structure, and it can have any. So it should be connected. So any two nodes. Any two populations should be connected somehow through using some path. But if you have disconnected networks, graphs, you can run algorithm for one part and the other like separately, I guess. But other than that, it's pretty general. Dense graphs. What do you mean by dense graph exactly?
Aneeq, I think maybe I can take a stab at answering that.
Sure.
I think the statement sparse graphs was to sort of distinguish it from the traditional mean field game setting where every agent can sort of talk to every other agent, where it's sort of completely connected. I think adding more connections, making it more dense, but not necessarily completely connected, would probably only have an impact computationally. I think actually we investigated this in the paper where we looked at a chain, so sort of three populations connected in a line versus a ring. And we found that the more connected one took maybe slightly longer to converge. So maybe that would imply that in denser graphs, things take longer to converge.
All right, thank you.
Yeah, I think that's good.
Okay, thanks. Thanos, I think you have a question, maybe.
Yes, I have. First, to continue what you were saying about the model-based, model-free. Like when you are model-based, the dynamics is very important. Like if this is not linear and the control doesn't enter in dynamics, then you might drift in different paths, and the best states might not be included in your training distribution. So then you will be very dependent on the training distribution, because if you only include sets that don't give you very good rewards, very low costs, then maybe it's not easy to construct the optimal path. There's no trajectories to the best. So I don't know. I always have this philosophical debate with François about model-based, model-free, and how much you can take from each one out. But my question would be, like, from what you initialize the parameters in the algorithm, like in the slide with the pseudocode.
Right. Yeah, I think this is it. So
yes. Okay. So if when you start from 0, then in your dynamics you will have like, because I was wondering if you start from a normal distribution, are you going to see something different? Like if you initialize your parameters from random.
So for the initial controller, for the linear part of the controller, we need stabilizing k. So I'm not sure if we initialize it to be like a normal distribution, I'm not sure if we'll get stabilizing. So this is something that's kind of standard in LQ setting, is that it's the linear part of controller. If it's not stabilizing, then your cost will go to infinity very fast. So yeah. So you need stabilizing k here. Other than that, for the second part of the algorithm, so one more, I guess, a small detail that probably I didn't mention is that there are two parts of the linear controller. So this is the offset, which is kept 0, and then there are two parts. The first part is the part which is linear with the state of the agent. The second part is linear with the mean field. So the part with the mean field is kept 0. So initially we start with a decoupled LQ cost. So basically, in the first iteration, we are doing a decoupled LQ RL. But from second iteration, what will happen is we'll have some value for the coupling with the mean field, and then the mean field will also not be 0. So then there will be a coupling that will start. So to answer your question, we absolutely do need a stabilizing controller for the linear part. And for the offset, we can start with anything. I think we can start with the normal initialization, or we haven't studied what's the best initialization. That would be an interesting idea, but we haven't studied that. Yeah, but you can initialize with basically anything for the offset. Yes, yeah.
Sorry, just to understand better, because I haven't seen before this stabilizing for the key. How does it work? How do you find the stabilizing?
Stabilizing k, yeah. So that's an interesting question, actually. Stabilizing k, I think. So in the LQ setting, stabilizing versus non-stabilizing control is very important because if you have a non-stabilizing control, your state will blow up. Basically, and then your cost will be really well. Your cost will actually be infinite if your state blows up. So stabilizing controller is something I think you find using trial and error. So for each agent, you can find a stabilizing control. You basically just pick a control and you apply it to the state of the agent. And if the state blows up, then you don't pick that. So I think that's one way of getting a stabilizing controller. But this is kind of standard in literature that they assume access to a stabilizing controller. But in essence, actually, if you look at it, it's also a kind of like a hard problem. But one way to look at it is you just pick a controller at random. You just have some. The controller is a matrix, right? So you just have some random matrix, and then you apply it to the system. If the state of the system blows up, then it's non-stabilizing. If it goes to 0, so it can be. The good thing about linear controller is that linear dynamics is that it will either blow up or it will converge to 0. So if it converges to 0, then it's a stabilizing controller.
Okay, thank you.
Yeah, thanks.
Okay, thanks. More questions or comments? Actually, in this algorithm, just to make sure I understand, so the mean field in the first part, for example, the mean field term, the Z bar, is updated at each iteration completely. So for example, you have Z bar 1 equals to 0, then you do the ZSO, you get the new controller, you deduce a new mean field Z bar 2, and this is your new candidate for the mean field. And then you compute again the new K, then you get the new mean field. So it's really like a pure fixed point somehow.
Yes,
so
yes.
Is this the reason? Okay, I think that's.
Yeah.
So is this the reason why you need strict contraction or okay?
Yeah, we need contraction for the mean field update to to converge. Yes.
And how do you check that? Do you need ks+1 to remain stabilizing at every iteration? And if yes, how do you guarantee that?
Yeah, so actually that can be shown to be stabilizing because of the simple reason that if k becomes unstabilizing, the cost actually goes to infinity. So if you start with the stabilizing k, then your cost in the ZSO can be shown to be strictly decreasing. So if the cost is decreasing, your controller is for sure stabilizing. Yeah. So k. Yeah. So k is stabilizing, and an effect of that is that the z bar will also be stable. So the z bar trajectory will also be stable. If the k is non-stabilizing, then z bar can actually blow up. So because of we start with the stabilizing k, and then our cost in the ZSO is strictly decreasing. So there are a lot of complications in the proof, and there are these small knots that need to be tied. So that's kind of taken care of in the proof. Yeah.
I see. And so the iterations you were showing at the end in the plots are the iterations of the outer loops, or it was also taken into account? Okay, I see. So inside each iteration, you do ZSO. Okay, makes sense. Thank you.
Yes.
I think one more question by Thanos, maybe.
Yes, to remain in this in the code, like if I remember correctly, when you said Z bar, it has some noise, some simulation noise. And what assumption do you have on this? Because if like this simulation noise is just a Brownian motion, then for sure that Z bar would visit infinity. Like it could visit infinity. In fact, if the W was a common Brownian motion, then
right, it can.
Because I remember that you had a linear structure. There was no kind of mean reversion or something on Z.
Right. So let me go back. So that's true. So the kind of structure we assume for the first part will have this structure. So it's linear. If you just look at this structure, and then there's a Gaussian noise. So in essence, it can approach. Well, I wouldn't say to approach infinity, but it can be unbounded. Yes, but because f, so I think as Matthew mentioned, because of stabilizing controllers, f is always stable. So what it means is that f will have eigenvalues less than 1, and what that means is that if omega for some time is very large, it will drive the z bar back to 0 because of stabilizing f.
Yes.
So it can, it can, that in essence, it can have very large values. Yeah. I think that. Thank you for the question.
Thank you for your explanation.
Sorry, just a follow-up question. So this omega t is a kind of common noise, or?
Omega t, yes, it's not a common noise. So the noise is due to our we say that the simulator simulates the behavior of the mean field, but it actually has access to a single agent dynamics. So
Z bar is kind of the estimate. Oh, sorry. Yeah, Z bar is a kind of estimate of the mean field, and it is random because you use a single, I think.
Yes, yeah. So the Z bar is the estimate, and then it will have this random noise due to the imperfect simulation. I mean, if you have a perfect simulator, you need access to infinitely many agents, which can basically simulate the aggregate of infinitely many agents. But we don't have access to that. So we have access to a single agent, and that brings in the noise.
Okay, thank you. More questions? All right. Well, if not, thank you again for the nice talk, and thank you, everyone.
Thank you for inviting me. Thank you guys for attending.